In this video, I want to talk about the ideal basic circuit elements that we will see in this course. So in this course, there are 5 ideal basic circuit elements. We have the voltage sources, we have the current sources, we have the resistors, the inductors, and finally we see the capacitors. So let's just go through them one by one. At least you can see how we can represent these 3 basic elements in our circuits. So for voltage sources, we have 2 types of voltage sources. We have independent voltage sources and we have dependent voltage sources. The same is true for current sources as well. We have independent and also dependent current sources. So for the independent voltage and current sources, we show them using circles. For voltage source, we use the positive and negative signs to show the polarity of the voltage source, and we usually write down the name or the value. For example, let's say if this was a 5-volt voltage source, we write down the name or the value right next to the source. The same is true for the current source too. We use a circle to show an independent current source. But here, since for the current, the direction of the current is important for us, we use an arrow to show the direction of the current. And similar to the voltage sources, we use the name or the value. For example, let's just say this one is 1 amp with the unit next to the current source. For dependent voltage and current sources, we use a diamond shape instead of this circle. So anywhere that you saw a diamond shape, you should immediately know that this is a dependent voltage or current source. If inside the diamond you have positive and negative sign showing the polarity of the source, that means that it is a voltage source. As you can see, these 2 top ones, these are both voltage sources, dependent voltage sources. If you have an arrow inside, that signifies that this is a dependent current source. As for the value, for the dependent sources, you usually have a relationship between the value of the you have a relationship for the value of that dependent source. I will go over it at a later slide. So for resistors, we use this jagged line to represent a resistor. We have 2 terminals. We use a positive and negative sign to represent the voltage at the 2 terminals. So if you go back to the previous lecture, you see that we said for the basic circuit elements in general, we usually consider them to have 2 terminals. So you can consider this to be terminal 1, this one to be terminal 2. And to represent the characteristics of this resistor, we need to know what is the voltage at the 2 terminals and also what is the current that goes through these 2 terminals. So for the current, like before, we use an arrow to show the direction of the current that goes through this resistor. For the inductors, the symbol that we use is like this. We use these half circles that are representative of the windings of a wire around a core, an inductor core, as the symbol for a generic inductor. Again, like the resistors, we can have these terminal numbers 1 and 2 to be able to specify the characteristics of an inductor. Same as resistors, we need to know what is the voltage across the 2 terminals of the resistor. the inductor, and also what is the current, which is shown using an arrow. So this arrow can be shown here too. So there is no specific reason for us to have the arrow here, right? I can show it here too, right? The only important thing is that the direction of the arrow specifies in what direction the current goes through the terminals of the inductor. And finally, we have this symbol for the capacitor. As you can see, this symbol is kind of broken in the middle, and this is because a capacitor in general, a basic capacitor, is created using two plates with a non-conductor between the two plates. So this gives the capacitor the capability to collect electric charge. So we will go over more details at a later lecture. But for now, just know that we use two plates like this. They can be completely parallel, or one of them can be curved a little bit like this to show a capacitor. Similar to the resistors and inductors, if we know the relationship between the voltage across the two terminals of the capacitor and the current that goes through it, so whether I show it here or I show it here or I show it here, they are all the same thing. I can explain all the information that I need for the capacitor. So the relationship between the voltage and the current explains all the properties of the capacitor. So now that we saw these, let's just go into a little bit more detail about the voltage and current sources. So what is an electrical source? So an electrical source is a device that is capable of converting non-electrical energy to electric energy and vice versa. So you probably can think of several examples. So for example, a battery is an electrical source because it is capable of converting chemical energy into electric energy. So for a battery, this direction is usually always the given, going from a chemical energy to electric energy. If the battery is rechargeable, then the other way is also possible, to basically connect the battery to, let's say, an outlet, and then because of some chemical reaction that happens inside the battery, you store the electric energy in a form of chemical energy inside the battery. Another example is a dynamo, which converts mechanical energy into electrical energy. So the important note about voltage and current sources is that these sources can either deliver or absorb electric power. Why do they both deliver and absorb? Because the end goal for electrical sources is that they need to maintain either a fixed voltage across the two terminals or a fixed current going through their terminals. I will explain this in a bit more detail at a later slide. So ideal sources are considered examples of active elements, which basically means that they are capable of generating electric energy. In contrast to active elements, we can have passive elements like resistors, inductors, and capacitors that they cannot generate electric energy. So voltage and current sources, they generate electric energy. Because of that, they are called active elements. But resistors and inductors and capacitors, they don't generate energy. and because of that they are called passive elements. So between the three of them, resistors, basic resistors, they always consume energy, but inductors and capacitors, they have the capability to store energy too, and they can provide that stored energy to the circuit too, given the right conditions in our circuit, right? So that is the difference between resistors and the inductors and capacitors, right? But nonetheless, none of them generate energy. So now let's just see how an ideal voltage source works. An ideal voltage source, as I said before, maintains a prescribed voltage across its terminals, regardless of the current flowing in those terminals. So if we have this ideal voltage source, again, since it's an independent voltage source, I use a circle, I use this positive and negative sign to show the polarity, I show the name or the value to the side of the voltage source, and for this I assume that I have a current that goes through the positive terminal of the voltage source. So as I said, the value for this voltage source is fixed. The voltage that this one provides is fixed. And this value should not depend on the amount of current that this voltage source is providing or even absorbing. So what does it mean? So let's just quickly draw a schematic for such an element. So this is the characteristic graph for an ideal voltage source. So on the horizontal line, we have the current, which is shown in ampere, and for the vertical line, we have the voltage, which is shown in volts. So when we say this ideal voltage source should provide or maintain a fixed voltage across its terminals, regardless of the current that goes through it, that means that the characteristic curve for this source is a straight line that is parallel to the horizontal line of the graph. So at any of these points, you see the voltage is fixed, but the current can be different. So we have, let's say, I1 here. In this point, we have I2 here. This thing can be even extended to the negative side too. So for example, at this point, we have a value, we call it I3, right? So no matter if this voltage source is providing current or absorbing current from the circuit, the voltage that it provides across its terminal is always fixed, right? So that is the defining factor for a voltage source. So because of that, if we have the voltage across a voltage source, there is no way that we can find how much current goes through the voltage source without basically solving the whole circuit. So there is no direct relationship between the voltage and the current of an ideal voltage source. For other elements, as you will see later, for resistors, inductors, and capacitors, there is a mathematical relationship between the voltage and the current at any given time. For the ideal sources, there is no such equation. So unless we solve the circuit as a whole, we don't know how much current is going through the ideal voltage source. So let's just do the same for the ideal current source and see how it works. So an ideal current source maintains a prescribed current through its terminals regardless of the voltage across those terminals. So again, we have this ideal source. I show it with a circle. Since this one is supposed to be a current source, I use the arrow to show the direction of the current. And for now, I assume that we have a positive voltage here and a negative voltage here. So this is just an assumption. So if I draw the characteristic curve for this ideal current source using the same coordinate system as before, with current being represented in the horizontal line and voltage being represented in the vertical line, the characteristic curve of this ideal current source is a vertical line that is parallel to the V coordinate. So again, like this, at any given point, you have always a fixed current, IS, but the value for the voltage can be different. So if you are at this point, the voltage here, you can call it V1. If you are here, the voltage can be V2. And you can even extend it to the negative side too. So for example here, you can call the voltage to be V3. So depending on the whole circuit, you can determine what is the voltage across the current source, right? But not by looking at the current source itself. So if all we have is the current flowing through an ideal current source, there is no equation that we can use to calculate the voltage drop across that source. That only can be done after we have solved the whole circuit. And based on what we get there, we can see how much current how much voltage we have across this current source. So let me just quickly show you an example so you know what I mean. So for now, let's just assume we have this basic circuit. I know I still haven't introduced the Ohm's law, but you probably have heard it before. So I assume that you have heard at least Ohm's law, and then I build upon that. So in this basic circuit, what we have is we have a 5-volt ideal voltage source, and this is connected in these two terminals to this 1 ohm. So this is the symbol for resistors. This is the unit of resistance. So this is 1 ohm. So the Ohm's law states that the voltage across any resistor. So if I just have this as VR equals the resistor itself, R, multiplied by the current that goes through the resistor. So let's just call this IR. So this is what is called the Ohm's law. I will explain this more later too. So now, since the voltage across these two terminals is 5 volts and the resistance is 1 ohm, what is the current? So this is very straightforward. The current is going to be 5 amps. So now let's just take a look at another circuit. Let's just keep the 5 volt here, and let's just connect it to a 10 ohm resistor. So again, we have here VR, here we have IR. So this Ohm's law always holds. So we have VR R multiplied by IR. But now, this time, we have VR to be 5, R to be 10, which makes the IR to be 0.1 amps. So as you can see, the value for the current that goes through the voltage source or to this circuit only can be determined after we have solved the Ohm's law equation for this very basic circuit, right? So even though we are using exactly the same ideal voltage sources, for this one the current is 5 amps, while for the this one is 0.5. This one is 0.5 amp. For the first one is 5 amp, while for the second one is 0.5 amp. So depending on the circuit that is connected to the voltage source, the current that goes through the voltage source changes. And unless we know that circuit, we cannot know how much current goes through the voltage source. The same analogy can be applied to the ideal current source too, that we may know how much current this ideal current source is providing, but we don't know what is the voltage across the two terminals unless we know how much of a current or how much of a voltage results in as the result of the circuit that is connected to this ideal current source. What about the independent? We talked about the independent sources. So what about the dependent sources? So an independent source is able to establish a voltage or current in a circuit without relying on any voltage or current elsewhere in the circuit. And they are shown with circles. On the other hand, dependent sources or controlled sources establish a voltage or current in the circuit, and the value for that voltage or current depends on the value of a voltage or current elsewhere in the circuit. So their value depends on a voltage or current in another place of the circuit. And as I said, they are usually shown with diamonds. So these are the two dependent voltage sources that we have. These are the two dependent current sources that we can have. So for the top left one, we have Vs equal mu Vx. So since we used Vx, that means that this voltage source depends on a voltage in another location of the circuit. So because of that, this is called a voltage controlled voltage source. So this one is a voltage controlled voltage source. What about this one? We have Vs to be equal rho Ix. So Ix signifies that we are using a current to determine the value for Vs. So because of that, this is called a current controlled voltage source. So the same analogy can be made for the dependent current sources too. So for the bottom left one, we have Is to be alpha Vx. So Vx is the voltage at another place in our circuit. So because of that, this is called a voltage controlled current source. And finally, this one we have Is equals beta Ix. So this is a current controlled current source. So to completely specify an ideal dependent source, there are three things that we need to know. The first thing is that what is the controlling voltage and current for this specific dependent source. So for example, here we have Vs equals mu Vx. We need to know what is Vx, or where in the circuit we have Vx. The second thing, we need to know what is the associated equation that shows the relationship between the two. Of course, here I assume that they have a linear relationship. So we have Vs equals mu Vx. So this is a linear constant. But what if you are working with a very complex circuit in which we have Vs to be equals mu Vx squared plus alpha Vy, right? So in this case, what we have is, this one is squared. What we have is a more complex relationship between Vx, Vy and the value for Vs, right? So we need to know this equation. For now, we only work with linear equation. So we only have one linear constant, right? But we need to know what is the linear equation that shows the relationship. And finally, the last thing, we need to know the reference polarity or direction for the controlling voltage or current. So here, what we have is we have the polarity of Vs, right? So let's say in our circuit, this is connected to a full circuit at which we have this resistor, I call it Rx, which has voltage Vx across it, right? So here we should know the polarity of Vx. Without these polarities, it is not possible for us to understand the true relationship between this dependent voltage source and the voltage that is controlling it, right? So because of that, if this circuit, if this resistor has a polarity like this, as opposed to having a polarity like this, so completely reversed, this results in two different solutions, right? So we need to know what is the reference polarity for the controlling voltage. The same is true for knowing the reference direction for the controlling current too. So for example here, let's say we have this resistor in our circuit, right, somewhere that has Ix going through it. So having it like this versus having it going backward, right? So let's say going like this. These are two different circuits and result in two different solutions. So we need to know that. So between these four cases, as you can see, we have four linear constants. We have mu, we have rho, we have alpha, and we have beta. So mu and beta are dimensionless because the variables on both sides both have the same unit. So here on the left we have voltage. On the right also we have the controlling voltage. So the controlling source is a voltage source. So voltage on both sides. So for this equation to be satisfied, all the units from the left hand side and right hand side should be exactly the same too. So because of that, mu is called a dimensionless or unitless constant. The same is true for beta as well. On the left side we have current, which is shown in amperes. On the right hand side we have Ix, again its unit is ampere. So because the two units on the two sides of the equation need to be the same, beta is unitless or dimensionless. You cannot say the same thing about alpha and rho. Why? Because the units are different on both sides, and these constants need to correct the unit as well. So here we have the unit on the left hand side to be volt, and the unit on the right hand side, the current, is amp. So because of that, for the units of both sides to be exactly the same, the unit for rho needs to be voltage over amp, or volt per amp. For this one, on the left we have the unit to be amp, and the unit for voltage is V. So because of that, the unit for alpha needs to be amp per volt. Of course, for the purpose of this course, knowing the units is not going to be that beneficial for us, right? Because it doesn't change the way that we solve these equations, right? But this is something that you should always have in mind, that when you are working with physical variables, like here we are working with voltages or we are working with currents, right? Anytime you have an equation that involves physical variables, the unit on the left hand side of the equation needs to be exactly the same to the unit on the right hand side. Otherwise it doesn't make sense. So for example, you cannot compare mass with time. You cannot compare length with gravity, for example, right? So when you have this equal sign in an equation that involves physical variables or physical parameters, the unit on the left hand side is equal to the unit on the right hand side. So in this video, we got introduced into 5 ideal basic circuit elements that we will see in this course. We saw voltage sources, how they are defined. We saw current sources, how they are defined, and what are the properties of independent voltage and current sources. And also we saw what are the properties of the dependent voltage and current sources. And also we saw the different types of dependent sources: voltage controlled voltage source, current controlled voltage source, current controlled current source, and voltage controlled current source. And also we saw the schematics that we will use for resistors, capacitors, and inductors.